Good morning, everyone, and thanks for sticking out until the last two sessions and the last day. So I was asked by the organizers to give a tutorial on on Shiba states and their use to realize topological superconductivity and Majorana bound states. And so I'm happily abiding by this request and will tell you what I understand about this subject over the next hour or so. Basically, all I know about it, I learned from discussions with my collaborators on this, and they are on the theory side, Yang Peng and Falko Pientka, who were PhD students and have since moved on to postdocs, Yuval Winkler, who was a postdoc and moved on to another postdoc, Leonid Glasman. And then we also enjoyed a lot of very nice collaboration with Katharina Franke's group. And in fact, most of this talk she should have been giving, because I'm just showing her data and telling stories about them. So you'll see along the way that much of what I'll tell is really based on her work. OK, so this talk will be mostly devoid of equations and technicalities. And I will also assume that you have some vague familiarity with Majorana bound states, as they have been discussed in this conference already several times. And if you want to read more on some of the technical details and some of the calculations that are underlying some of the things that I will be telling, then you can look at these Les Houches lecture notes that I wrote up together with Yang and Falko a couple of years ago. So they're not really entirely up to date, but they contain many of the basics that I'll be using. OK, so of course, one of the major reasons why some of us are interested in this subject is that everyone is talking about using Majorana bound states for topological quantum computation. And recently, Microsoft announced that they are seriously trying to pursue this. And some of us watched some advertisement video last night that they put out that is quite amazing. I won't show it here. So what I will talk about today is actually not what they are pursuing. They are trying to pursue this semiconductor quantum wire platform. The platform that I will discuss today is probably ill-suited for quantum computation applications. I might get back to it in the end why that is. And so I will talk about these magnetic adatoms that were really pioneered by Ali Yazdani's group together with Andrej Brnevik. And so I will start with discussing these experiments. And I'm sure, although I wasn't there for those talks, these have already been discussed. These data have already been discussed at some level in previous talks. OK, so here are the basic experimental slides from the paper by Ali Yazdani's group. The reason why this is a good platform for hunting for topological superconductivity and Majorana bound states is that it really includes the three ingredients that we know now are needed in order to realize the underlying topological p-wave, spinless p-wave superconductors that are showing this kind of physics. And these three ingredients that make up this sort of magic recipe are the following three. Basically, you need some sort of conventional superconductor that provides you with S-wave superconductivity, although you want to get to p-wave superconductivity. Then you have to somehow spin polarize the system in order to make it close to a spinless system. And then finally, in order to match these two things, spin polarization and conventional superconductivity, of course, don't really go together very well because you have spin-singlet superconductors. And the spin-singlet superconductors cannot enter into a spin-polarized system because one electron will be frustrated. And in order to kind of make this match and produce the necessary p-wave correlations, you need spin-orbit coupling, which makes spin not a perfectly good quantum number. And then these almost spin-singlet Cooper pairs can talk to your spin-polarized system. Now, in these magnetic adatom chains, you obviously have these three ingredients. The superconductivity comes from the from the substrate, which in these experiments is often lead. Then you have spin polarization because you're using magnetic adatoms, and they typically order magnetically, at least on these short length scales, and that provides you a spin polarized bands of electrons. And finally, you have spin orbit coupling because the substrate is relatively heavy, and lead is thus expected to have substantial spin orbit coupling, and so you have all these three ingredients to make up a topological superconductor. The typical samples have these sorts of structures. They are chains that form spontaneously on these substrates out of blobs that you deposit on it, and this you just have to heat it a little bit and probably do a lot of more things that I don't understand, and then they form these chains. They typically grow out of these blobs, and so as you remember, Majorana show up at the ends of these chains, but you really have only one end that is pristine. The other end is kind of merged with these blobs, so we will always just look at Majorana signatures at one of these ends. They are typically, I guess this scale bar here, this is a few nanometers. I don't know, probably it's maybe it's 1 nanometer, maybe it's 10. But anyway, so these are typically a few tens of atoms long, these chains. Okay, so here are the initial observations. Basically, one of the great things about these systems is that you can look at them by SDM. So you have not only energy resolution, you also have spatial resolution. And you expect that Majorana bound states appear as zero bias peaks because they are zero energy states in the middle of the gap. And you can do this now both at the end of these chains and in the middle of these chains. And if you look at the middle of these chains, you get various subgap peaks. So the zero bias is the central dashed line here. The gap, superconducting gap, is limited by these outer dashed lines. This is the bias that you apply, and this is the tunneling conductance. Well, maybe let's start with the pristine surface. Then you see just a tight, nice BCS density of states. If you look in the center of these chains, then you see subgap peaks, but at zero bias, there is nothing particular. But if you look at the ends of these chains, then you actually have zero bias peaks showing up. One of the important things that I'll come back to later is that it seems that these peaks are localized very much at the end of the chain. So here, the difference in spatial difference between these two points here, this one and this one, is just 1 nanometer. And so within 1 nanometer, these peaks appear to disappear. So if there's a Majorana bound state, it has to be localized on the scale of about 1 nanometer at the end of the chain. You can also do this in color plots. And so this is at different bias voltages, and you see at zero bias, there's most of it is localized at the end of the chain, and there is very little amplitude in the bulk of the chain. These experiments have been repeated with various degrees of success by Katharina Franke's group and by the Basel group. This is actually published by now. I should change this. Okay, good. Another important point is that is the magnetic order of these adatoms on the surfaces. And it seems from the experiment that essentially these adatoms seem to order ferromagnetically along these short chains. So it may be short-range order, not real long-range order, but there seems to be ferromagnetic order. Okay, so that's the basic observation. More recently, Ali Aslani's group has also done higher resolution measurements, which basically means that he did the same experiments, but at roughly 1/4 of the temperature. So these are 250 millikelvin experiments rather than 1 Kelvin experiments. Here again is just a pristine surface. There, for lead, sometimes has these two different gaps, which are presumably associated with 2 bands. And then in these data, there's much more pronounced zero bias peaks at the end of the chain than I showed on the previous slide, whereas there is no such zero bias peak, or only very weak ones that are sort of at the noise level in the middle of the chain. So this is these higher resolution experiments seem to confirm the earlier measurements.
What's all those other things?
These guys?
Yeah.
So there's nothing wrong with having other subgap states. So there can be Shiba states, there can be
But shouldn't they be symmetric?
And this is a long story. It's basically another talk, and I'm not sure that I will get back to symmetry. No, they should not be symmetric. It's basically, depending on what you measure the electron wave function or the whole wave function of these subgap states, depending on the bias, and they can be different. Okay? It's a long story. You can talk a lot longer about this, but I don't want to get into it right now. But it's perfectly okay that they're not symmetric. Good. So then let me first emphasize two of the essential problems that one may have with these kinds of, or one essential problem that one can have with these experiments, and another one that came up later. So I already emphasized that these Majorana bound states are very, very localized. Now people had an expectation of how localized these Majorana bound states should be, and the expectation was that the localization length would basically be given by the coherence length of the topological superconductor that you form, and the topological superconductor in this chain, this coherence length is made up out of the Fermi wavelength of the electrons in this chain, which let's assume is some sort of metallic Fermi velocity, not Fermi wavelength, Fermi velocity of the order of 10 to the 6 meters per second. And then there is the topological gap that you're inducing in this chain. Now this gap cannot possibly be bigger than the gap in the proximity providing superconductor, which is the lead. And so this can at best be as small as the coherence length of lead. And if you do this, then you get something of 100 nanometers or so, if you estimate what these numbers are. But the real localization length in the experiment is 1 nanometer. So we are 2 orders of magnitudes off from in between the theory and experiment. So that's one thing. And several people, including Shankar Das Sarma and Patrick Lee, pointed this out very quickly after these experiments came out. Another question is that more recently Katharina's group has managed to also do cobalt chains on lead. So cobalt is not very different. It's magnetic. It just has one more d electron compared to iron. You can check that they are again spin polarized. They have this ferromagnetic order. It seems to be all the same. All the ingredients are the same, but there are apparently no Majorana peaks in that system. So one might want to understand this as well. Okay, so let me remind you then, because this is how we can understand some of these chains, about the paradigmatic model for a topological superconductor, and that's the Kitaev chain. So these Majorana bound states, the simplest system in which they show up in one dimension, are spinless p-wave superconductors, and the absolutely simplest model that you can make of such spinless p-wave superconductors is this Kitaev chain. So basically you imagine that you have a set of sites that are labeled here by I. On each site there's a single fermionic state that can be empty or occupied. There's no spin, so no double degeneracy or so because of spin. The electron, these fermions, these spinless fermions can hop between nearest neighbor sites. So this is this first term. If you had only this first term, this would just form the usual cosine band with a bandwidth that is given by the hopping. And then you assume that there is some p-wave superconducting order. Now, it necessarily has to be p-wave because you have to satisfy Pauli's principle, and the Cooper pairs should be odd under interchange of the fermions. And so since you cannot put 2 of these fermions on the same site, basically you have to put the 2 fermions on neighboring sites. That's the simplest thing that you can do. And so you add such a Cooper pair to neighboring sites, or you subtract it from neighboring sites. And this has some pairing amplitude delta. And finally, there's some chemical potential that just tells you how far you're filling this normal state band. Okay? And it turns out that this simple model has 2 phases, a topological phase and a non-topological phase. Whenever the Fermi energy is within the normal state band, then the system is in a topological phase. But if you deplete the system or you completely fill the band, then it goes into a non-topological phase. And it's kind of natural that if you don't have electrons or if you don't have fermions, then you cannot have a topological phase. So if you put the Fermi energy down here or you put it somewhere up here above the band edge, then you're in a non-topological phase. And these Majoranas show up whenever you have a domain wall between this topological and the non-topological phase. So imagine that you deplete some part of this chain, say, and then you're in the non-topological phase, and you have some part that is undepleted, and then there would be a Majorana bound state sitting here. And the simplest system that is depleted is just the outside the wire. There are no electrons, so the ends of these wires, if the rest of the wires in the topological phase, should have Majorana bound states. Okay. And you can see this quite explicitly by just solving this Kitaev chain for a finite number of sites. I'm not going to go through the details, but for those who've seen this before, it's kind of convenient to look at two representative cases. One is the case in which the chemical potential is just sent to -infinity. So basically, you're totally depleting the wire. Then the eigenstates are just electrons that are fermions that are localized on each one of these sites. And you can sort of entertain yourself by writing each of the fermion operators associated with the sites in terms of their kind of real part and imaginary part, or Hermitian part and anti-Hermitian part. Then it turns out that these gammas are Majorana fermion operators. But in this case, if mu is -infinity, then you combine two of these Majorana fermions into an ordinary fermion that is localized on each of the original sites. But conversely, if you go at another place in the phase diagram where the hopping is equal to the pairing and you set the chemical potential equal to 0, then it turns out that you get the same kind of free fermion Hamiltonian, but not if you pair the two Majoranas from the same site, but rather you pair them from neighboring sites. You take the real part, or the imaginary part from one side, and the real part from the other side, and combine those into an ordinary fermion operator. And if you do this on a finite chain, then now these two blobs came from the original site. This is the real part and the imaginary part. And now you're combining those two guys into a new fermion, and so on and so forth. But if you do this, then the first guy is going to be left out, and the last guy is going to be left out. And those do not appear in the Hamiltonian and correspond to the zero energy Majorana bound states that you have at the ends of these chains. Okay, so it's like kind of a dimerization transition between two kinds of dimerizations for these Majorana operators that you can make out of the original fermion operators. Good. So we will just see this model several times along the way. Good. So now let's try to understand these chains. And the first step that we have to take is to just understand what an individual adatom does on a superconductor. This is a classic problem of superconductivity, and was first looked at by Yu, Shiba, and Rusinov in independent papers. Here's the one by Shiba. And so in principle, such a magnetic impurity has anything that's magnetic about it comes from the d levels, and they are spin split because this is a magnetic impurity. So you have spin up levels that are presumably very low in energy, and spin down levels that are very high in energy and empty. The spin up levels are occupied. And now you put this into a superconductor, and the superconductor has some Fermi energy, and it has a gap around the Fermi energy. Okay. So now if these iron D levels are very far from the Fermi energy of the substrate superconductor, then basically we can ignore all kinds of charge fluctuations that are going on in the system, and we can just describe this impurity in terms of its local magnetic moment that is exchange coupled to the electrons in the superconductor, and this is an entirely local interaction at the position of the impurity. In addition to this exchange coupling, any of these impurities will also have some potential scattering that does not affect the spin in addition to this exchange coupling. Okay. And let's also assume, to keep things simple, that we can really treat this magnetic impurity as a classical spin. And so if you're worried about Kondo, let's just assume that the superconducting pairing strength is much larger than the Kondo temperature. And in that case, Kondo is just frustrated by the fact that you have a gap about the Fermi energy and you don't develop the Kondo effect. So if you just go and solve this problem of such a magnetic impurity in a superconductor, then you find that this just induces exactly one bound state below the gap, plus its particle-hole conjugate partner. So you have one bound state at plus energy E naught, which is within the gap, and the corresponding partner at minus that energy. It's very easy to calculate where this energy is in terms of the strength of the exchange coupling and the strength of the potential scattering. These are just dimensionless measures of J and V. You can also work out what the wave functions are of these bound states. They ultimately decay exponentially on the scale of the coherence length, some energy-dependent coherence length of the superconductor. And below this scale, they just fall off as 1 over r in 3D and 1 over square root r in 2e, and they oscillate with the Fermi wavelength of the substrate superconductor. And finally, these bound states are perfectly spin polarized. So there's only one spin polarized bound state here, and there are not two of these Shiba states for the two different spin directions. Okay? That's what you find if you solve this little problem.
Excuse me.
Yes.
So psi E, is it psi at the energy of the Shiba state, or?
Yeah, sure. So it's psi and then some square root of delta squared minus E squared factor. So if the closer you go to the gap edge, the bigger this psi becomes.
Okay, so basically what you should put is the E0 there.
Right? And the E, you do it at the energy of the Shiba state. Absolutely, yes. So this E is the same E as that E. Okay, good. And this E0 is the same as this E. Okay, so then it was Ali Asani a couple of, 20 years ago that first looked at these things with STM. And so he looked at manganese and gadolinium and silver for something that is non-magnetic. And then these are just the DIDVs minus the one of the pristine surface. So all you see are the subgap features. And you see that there are additional peaks showing up below the gap. And these are supposedly these Shiba states. Note that they're also asymmetric between positive and negative biases. These peaks show up both for manganese and for gadolinium, but they don't show up for silver because silver is non-magnetic, and then Anderson's theorem forbids the formation of bound states. Okay?
What was the substrate in that case?
Pardon?
What was the substrate in this?
What was the substrate? Was niobium. Okay, and if you look at the bare niobium, then you get a nice BCS density of states. These, I think, were 4 Kelvin experiments, so it's a bit more rounded than some of the later experiments. You can also, the resolution got a lot better in the meantime. Here's, again, Katharina Franke's data, and one of the things you can do is you can use superconducting tips, and then you see that there are much sharper Shiba states shown. And there's also not just one Shiba state, but there can be several of these Shiba states. Here, there's at least 2 resonances, alpha and beta, at different energies, and I may get back to that. Okay, good. So now we understand everything about individual impurities. Not everything, but a lot. Let's go and try to put them together into chains. And there are sort of two, or there's one basic thing that happens. Now, if we put 2 of these, or several of these adatoms onto the substrate in a chain, then the first thing that can happen, let's start here actually, is that the iron D levels start to overlap at some level. And so instead of having just individual iron D levels, they will form out into bands. And actually, the physics depends a little bit on how strong this band formation is. So these are now 1D bands, because these iron D levels are just with these adatoms are lined up along one dimension. Here are these one-dimensional bands. There is one band for the spin-up electrons, and there's a second band for the spin-down electrons. Let's forget about the fact that they're d levels right now. Let's just assume that it's a single level that has spin-up and spin-down for simplicity. I might get back to the d levels later on. And if these adatoms are strongly very close to each other and the iron d levels are very close and hybridize strongly, then this dispersion will be very strong. And if these iron adatoms are far from one another compared to their atomic radii, then the d levels will only hybridize very weakly. And in that case, you'll have only a very small dispersion. Now, if you, there are two things that can happen. If you have only very weak dispersion, then these iron d levels will stay very far from the Fermi energy of the superconductor at all case. Okay? And so basically, there's no charge fluctuations at all in this case. These bands are still fully occupied, and these ones are fully empty. Of course, conversely, if these d levels hybridize very strongly, then what can happen is that these iron d levels, d bands, actually start to overlap with the Fermi energy of the superconductor. Okay? And so, for example, you could have a situation in which the spin-up levels, d levels, are fully occupied because they are sitting below the Fermi energy of the superconductor, whereas the iron d level, spin-down levels cross the Fermi energy, so some of them now are occupied and some of them are empty. Now remember that we are after spinless or strongly spin-polarized electrons. Now this already looks very, very good to realize topological superconductivity. Because we basically, at the Fermi energy, we only have spin-down electrons. The spin-up electrons are totally frozen out because they're far from the Fermi energy. Okay, so these two limits, you can understand the physics in different ways. So even though the d levels of the iron do not overlap in this case, it may still be that the Shiba states, which only decay as 1 over r and really decay only after coherence length, may still be overlapping. So we may still form bands of Shiba states in that case, whereas in this case, the physics should be properly described by these low energy excitations that you get from the iron d bands. Now, you can describe all of this in terms of a single model, which is just a chain of Anderson impurities that you on the substrate. So you have some d levels. There's some on-site repulsion. There's some hopping between neighboring iron d levels. There's hybridization between the d levels and the substrate superconductor. And then you have a BCS Hamiltonian for the substrate superconductor. And if you then follow the experiment and simply assume that these iron d levels order magnetically, and you treat this magnetic order at simple mean field level, then you can solve this Hamiltonian very, very simply, and you can find what the phase diagram is and when it is topological and when it is trivial. And here is the result. So to understand this plot, this is the basically the Shiba energy of the individual impurity. Here is the band gap. Here's the center of the band gap. So this is the Fermi energy of the superconductor. This is delta. So the bigger the exchange coupling, the closer you move to 0 or even below 0. And this axis is the hybridization between neighboring iron d levels. So if you go through this, then and anything that's colored red or green is in the topological phase. Okay, and everything that is colored blue is trivial.
I'm confused about your error of the Shiba limit. That's not topological.
Pardon?
Is the Shiba limit topological?
That's also topological, actually. I'll get back to this. So the point is that the Shiba limit is, as we said, it's weak hybridization between the iron d levels. So this is at this end. So if the exchange coupling is strong enough that the Shiba levels are close enough to the center of the gap, then the system is topological. And this is when you have this situation. So the d bands are far from the Fermi energy of the superconductor. Conversely, you have the wire limit, or what I call the wire limit, in which you have one of these bands crossing the spin down band, say, crossing the Fermi energy. And this is happening here. You see you have very strong hybridization between neighboring I and D levels, but you can have arbitrarily weak exchange coupling for the individual impurities with a superconductor. And finally, if you make the iron hybridization very strong, then both spin up and spin down bands will cross the Fermi energy, and then you kind of expect that topological superconductivity goes away because you know that this should be a spin polarized system, and this one is no longer spin polarized. Or in other words,
is there spin orbit there? So do you need spin orbit?
You always need spin orbit, yes.
Ah, okay. So it's where it's sitting in the Hamiltonian.
In the Hamiltonian, you should add it into the substrate superconductor. I didn't write the Hamiltonian for that Hamiltonian for that reason. Okay. There's always the other story that you could also assume that there is some spiral, and that's unitarily equivalent to putting spin orbit into the substrate.
Somehow it seems counterintuitive that there's no break in your color picture between the lower left and the upper right.
It's the same topological phase. Actually, the red and the green is also more or less an artifact of the model. It still has some chiral symmetry that will probably not be there in the real case. So that will just be one topological phase in a realistic model, I would guess. Okay. So I guess let me just explain. So this I think is pretty obvious by now that it can lead to this topological phase. But let me briefly explain why this limit also leads to a topological phase. And so the way to describe this is now that we can basically ignore the fact that the I and D levels are hybridizing, and all you have is the hybridization of the Shiba states. And if these Shiba states are sufficiently deep, so we are close to the Shiba states are close to the center of the gap, then we can just project out the quasi-particle continuum. It doesn't matter, it's far away in energy. And these weakly hybridized Shiba states will then form, this is supposed to be states, I don't know what I did there. They form bands, so they also broaden out into bands. And now imagine that these bands cross the Fermi energy. Then it turns out that you basically have, and the states basically are made up, I mean, they are in a superconductor, so you will again induce some kind of p-wave pairing if you have sufficient spin orbit coupling. And so if these Shiba bands cross the Fermi energy, then basically you open an additional p-wave gap between the positive energy Shiba band and the negative energy Shiba band, and the system becomes a topological superconductor. And the reason it does that is that it's basically the same model as the Kitaev chain. You have a Shiba state at energy E0 that you can occupy or empty, and if you go to a Bogoliubov with the Gen picture, this is just E0 and minus E0. You have two of these states, so at each side you have one of these Shiba states. You can hybridize between neighboring Shiba states, so you can hop. And because you're in a superconductor, and in any case they are already wave functions that have particle and whole component, you can also have pairing correlations between neighboring Shiba states. Okay? And this is exactly the same Hamiltonian as the Kitaev chain. And so if this energy of the Shiba state is such that the Fermi energy, the center of the gap, falls into the band of these Shiba states, then you get topological superconductivity, just as in the Kitaev chain. It's exactly the same. And there's only one little thing that I'm shoving under the rug, and this is that these Shiba states are actually decaying only like 1/r for all practical purposes, and so there will be long-range hopping and there will be long-range pairing. So the fact that it's only nearest neighbor hopping and nearest neighbor pairing is really not quite right, and this is something that one should check, and you do check, and then you find this kind of these kinds of pictures. Okay, so it's topological because it's the same model as we've been discussing early on. Okay, then there's the wire limit, and so if you have basically all there is to it is that it's some continuum version of the Kitaev chain. So if you had the Kitaev chain, and this is your dispersion of a Kitaev chain, and you say the Fermi energy was close to the lower band edge, then you could just make a p-squared approximation here, and then you get some continuum version of the Kitaev chain, and that has a topological phase when the chemical potential falls into the band, and it's trivial when it's outside the band. So again, it's exactly the same kind of physics as before.
So
yeah.
So how does the spin orbit show up in these Hamiltonians? I don't see something.
Where it is?
It's hidden somehow.
It's hidden in this delta and this delta prime in the pairing amplitude. this pairing amplitude would be strictly 0 if there was no spin orbit, because it's sitting on neighboring. Here it's psi dagger, gradient psi dagger, and here it's Cj plus 1. This is supposed to be j. So these are neighboring sites. And in order to get these correlations, you need spin orbit. Without spin orbit, they would be strictly 0. And pure S wave you cannot get because there's only a single spin component.
For P wave and the T wave, you have this also the capacity naming sense.
Right, but for D wave it would be more complicated than this. Right, this is a single.
But in this case, you want to do it just
for D wave.
Yeah,
no, for D wave it would be different. But
you have the same type of pairing word.
but not exactly the same. This is P wave.
No, but I mean P wave is probably just as well.
Because if you
Also P wave without spin orbit.
so D wave, I must admit,
So there must be some additional terms which include spin orbit.
no, it's the way that if you need the spin orbit in the substrate superconductor in order to have these amplitudes. You would, if you didn't have spin orbit, this delta would be strictly 0.
Just a P wave superconductor.
No, the substrate is an S wave superconductor. And,
So you say
and in order to generate effect,
okay, the argument is for you that in order to generate this,
I need spin orbit. Yes. So if I want to get this microscopically, I do have to have spin orbit coupling somewhere in my system, or I need to have some spin spiral. Yeah.
Because that he's integrated out. This
yeah.
wave, and now it's part of the Hamiltonian.
But not any spin orbit, right? Because I mean, in LED, you will say you have an isotropic spin orbit coupling. This would be not make. I mean.
No. So yeah, actually, you need Rashba type of spin orbit in order. So anything that is inversion symmetric is not going to do the trick for you. Yes, absolutely.
You need the
Yeah. So it needs to be Rashba coupling, or the adatoms need to break their position of the adatoms need to break inversion symmetry in the host superconductor. Yes, absolutely.
Okay. Can you then tell that, let's say, you take niobium or lead, or so how large the delta should be? I mean, is there some quantity in the bulk superconductor itself that?
Well, in order to be in the topological phase or not, all you need is that this dispersion is strong enough such that the bands actually cross the Fermi energy of the superconductor.
Yeah.
Okay. But delta then, of course, determines how big is the gap of that topological phase and how likely are you to see any consequences of it.
I'm asking a different question. I mean, let's say I'm an experimentalist who wants to design this.
Yes.
I would like to know what is the value of delta. And let's say you have the house superconductor, you say that, okay, if there is no spin orbit, this delta is actually 0.
It's 0.
Even though it's the delta of the superconductor is finite. So how
Right.
much, I mean, how do I know?
I think the most honest answer is that at this point no one really knows how big it is. You can try from some of the subgap spectra to get an upper bound on what this delta might be, and it's probably something of a tenth of the bulk gap.
So for example, for niobium, how large is delta?
For niobium, I would have no idea. Because no one did the experiment. But for lead, it seems that at best, this induced gap is of the order of a tenth of the order of magnitude, 10% of the bulk gap of lead.
Okay.
Yeah. But again, this is not something that has been pinned down with great accuracy. Okay. Okay. Good. So then let me let's see how well. Okay. I mentioned in the beginning that one of the big problems of this experiment is the strong localization, and for that we need to be a bit more careful with understanding the proximity effect that is going on. And let me not go through much of the technicalities, but just give you a reason for how we might possibly understand the strong localization. Well, actually, the theory, I think, is completely good. The question is whether it describes the experiment. I don't know. So remember that the basic problem was that we expected the localization length of the Majoranas to be determined by the Fermi velocity of this 1D band, which I argued was some kind of metallic Fermi velocity, and the topological gap, which we just discussed, was roughly 10% of a lead gap, but maybe at least something on that order. Now, that gives a factor of is a factor of 100 off compared to the experiments. And the solution to this, or one possible solution to this, is that this might be you can get this in the right order of magnitude if you take account of the fact that in this case, this 1D system is actually very strongly coupled to the substrate superconductor, because you have these iron atoms that are basically sitting in the lead matrix, and it's sort of atomic physics or high energy condensed matter physics scales that are determining this coupling. So if you now imagine that you have a subgap excitation in this one-dimensional chain, okay, so subgap relative to the superconductor, then this excitation cannot decay into the superconductor, but it can virtually enter into the superconductor, and it will very much like to do this because of the strong coupling, and the timescale that is associated with it is given by the strength of the coupling, and which I denote here by gamma. And the strength of the coupling, as I said, it's atomic physics, so it's going to be of the order of an electron volt or so. Then this excitation will virtually stay in the bulk as a subgap excitation in the bulk superconductor. Now, the timescale over which this excitation can do that is related to the fundamental timescale of the superconductor, which is the gap. Okay, so the timescale will be 1 over the gap, and then this excitation will just go back into the 1D band of the adatoms. Okay? And this will repeat. And now what you see is that actually this excitation basically spends all of its time in the bulk superconductor virtually, and almost none of its time in this 1D chain. Okay? So because delta is so much smaller than gamma, okay, it's about a factor 1,000 smaller than gamma. So actually only one part in 1,000 this excitation is spending in this 1D chain, and the rest of its time it's spending in the bulk superconductor. More technical way of saying it is that the bulk part of the spectral weight of this excitation is living in the superconductor and not in the 1D wire. And if you now make the somewhat crazy but actually correct assumption that this excitation can only travel along the wire when it is actually in the wire, and it's basically enters the superconductor and leaves the superconductor at exactly the same place, okay? Then you see that your effective velocity with which you're moving along this wire is reduced by a factor of 1,000 compared to the bare Fermi velocity of the wire. So basically there's a Fermi velocity renormalization by about a factor of 1,000 compared to the estimate that I gave you in the beginning. And then on top of it, delta top, the topological gap is about 10% of the bulk gap. And if you put these numbers in, which again, admittedly, is just like this, you get something that is 2 orders of magnitude smaller than the initial estimate, and that's actually consistent with the experiment. Now, you may not believe this argument because some parts of it sound crazy, but it's actually not crazy, and it's very simple to do a little calculation. And I promised some people yesterday that I would have no equations in this talk other than Kitaev chain. This one slide is, and I will not talk about it, but you do some simple calculations with the Green's function, and you find that there is, for those who understand, basically there is some quasi-particle renormalization because of all of this spectral weight is living in the superconductor. But this quasi-particle renormalization also shows up in the effective Hamiltonian terms of the 1D system and renormalizes the Fermi velocity. So you can just do a simple calculation that just verifies this picture. The reason why everything in the superconductor is very local is because you have to sum the self-energy over all the transverse wave vectors, and the resulting self-energy due to the excursions into the superconductor is basically wave vector independent, and that means in real space that it's extremely local. So that's why you're not propagating in the superconductor. Good, and you can check this numerically with this original model, and these Majorana wave functions have exactly the right localization lengths compared to the expectations from this kind of estimates, and you can look at the subgap bands, and they also do exactly what you want. Good. So this is, explains why they are so localized, or it's one possible explanation for why they are so localized. Good. But are they really Majoranas? Do we have more things that we can check whether they are Majoranas or not? And so there are 2 typical things that people, or there one thing that we can say. So spectral and spatial resolution, they say, are okay. But there's another thing that people always expect, and that is that the conductance is quantized if you tunnel into a Majorana at 2e²/h. And as with most other, except for very recent experiments, this is definitely not a quantized peak. It's much below this. And presumably, this is due to thermal broadening and quasi-particle poisoning processes that suppress the conductance peak below 2e²/h. But you can do a little bit better, and that is when you use superconducting tips. And now I'm getting back to the symmetry issue. So there are several things. If you take a superconducting tip, there are several things that one should that are working in one's favor. The first one is that at least thermal quasi-particles are strongly suppressed because now the tip also has a superconducting gap. And so there's the thermal broadening of the tip is much less significant. The second important thing is that now if you want to tunnel from the superconducting tip into such a Majorana end state, then you always have to break a Cooper pair in the tip. And this means that the Majorana bound state no longer appears as a zero bias peak. That's important. It's no longer a zero bias peak. But you always have to provide this energy to break up the pair. So the peak now appears at plus or minus the delta of the tip, the gap of the tip. Okay? And you can either pull electrons out and tunnel them into the tip, or you can tunnel them from the tip into the in the substrate. And so you have two of these peaks. And if you have two peaks, you can not only ask about how high is the peak, you can also ask about how symmetric are these peaks. So now there's the symmetry. Okay? And while for general Shiba states they are not symmetric, and we've already seen pictures of this, it turns out that for Majoranas there's very good reason to believe that they should always be symmetric. And the reason simply is that Majoranas are really particle hole symmetric wave functions. For them, U is equal to V, or V star to be more accurate. Okay? And moreover, the tip is also perfectly symmetric. And here I just convince you of this by showing you experimental data for normal tip tunneling into a superconducting substrate. And it's perfectly symmetric. If you do this with a superconducting tip, then again, it's perfectly symmetric. So the tip also doesn't break the symmetry. So if these are Majorana peaks, they should be symmetric. Now, actually, Yastani already did this experiment early on with a superconducting tip in the first paper, but he only showed from 0 to 2. He didn't show the other half, the negative bias one. So Katharina did that experiment, and here's the data, and it's not symmetric. These are these two peaks, not symmetric. Well, I don't want to get into it. This is not so obvious that this is really just single peaks. If you draw it like this, it looks like beautiful peaks. If you plot it like this, it's not so obvious whether these aren't two peaks that are overlapping. So you can weasel your way out of this. And this might still be consistent because the asymmetry comes from some other peaks that are very close by because the induced gap is so small. And more recently, Ali did this high-resolution paper that I already mentioned, and they checked this more carefully. And in some samples, at least, these peaks seem to be nicely symmetric. And you can also overlay these plots, and they come out symmetric. But how systematic this is, I don't know, but there are at least some samples in which they come out very nicely symmetric. Okay? So we shouldn't throw this out altogether yet. Good. Just to mention this, you can also work out this conductance quantization now for a superconducting tip, and it's not 2e²/h, but rather it's 4 minus pi 2e²/h. This is harder to measure than the symmetry. It's also less robust than the symmetry, so this no one has seen at this point. Okay, good. So then let me...
Can I ask a question actually here?
Yes, sure.
But if you have a conductance this high, and the voltage is of the order of the size of the, basically it's just the order of delta.
Yes.
You are putting a lot of power to your small system. Shouldn't you care about this power?
Say it again. Why would you? It doesn't depend. I mean, it depends.
You have dissipated power.
Well,
it doesn't dissipate. You have the wire is on top of a superconductor.
Right.
And as you know, superconductors are extremely poor carriers of heat.
Right. Yeah, you should probably
Where
avoid.
does the power go?
Yeah, but in reality, people are very far from this limit at this point.
Maybe they are far from this because of the dissipation.
Maybe. I mean, so in the let me put it this way. So for the normal state tips or normal state leads, people now do get 2e squared over h. So both Leo Kauenhoven and Charlie Marcus have data where they do get to 2e squared over h, and they claim it works. How convincing these data are is another question, but they do seem to see 2e squared over h. I haven't thought about the power dissipation at this point. It may be interesting. Okay, so so far I always pretended that there was only a single Shiba state. Actually, we already saw some data that show that there are several Shibas resonances below the gap, even for an individual impurity. And here are some of them. You can actually look at the maps in STM of these states, and they kind of have, here it's maybe the best one, they have this d-wave, d-orbital shape. So here is a dz squared orbital. This one is supposed to be xy or xz and yz superposition, and this would be x squared minus y squared, plus some other features that are much weaker that come from the symmetry of the substrate. And it turns out that for manganese on lead, you can actually understand this quite nicely, because manganese is supposedly has supposedly 5, it's 2+, and it supposedly has 5 electrons in the d shell, so it's completely isotropic. So it forms an overall S state, and this one S state, if you work it out, actually scatters only in the L equal 2 channel. Actually the Shiba states, unlike the simple model, are not due to scattering in the S wave channel, but due to scattering in the L equal 2 channel. And then you have again this d orbital physics, and you can look at how at the ligand field for this adatom in its surrounding matrix, and you can understand that in this case, due to symmetry, this should basically split into 3 peaks that have exactly these symmetries. So this seems to work out very nicely and explain why there's sometimes several of these Shiba states. You can also do this with dimers, and then they should split into symmetric and antisymmetric versions. And if you look at the maps, these are again Katarina's data, then you see that this seems to be nicely consistent with expectations. Okay, so so far, whenever I was talking about d levels, I only had spin up and spin down level, and there was no d levels at all. But now let's go one step beyond, and we now have this chain of iron d levels. Now the irons are also d levels, and they're also really 5 spin up levels and 5 spin down levels. Now this is not because of hybridization of Shiba states, but because of hybridization of the iron d levels. And so the band structure doesn't look like this, but this is something that is due to Ali Astani's group and Alan MacDonald and Andrei Bernovic. So there are simply 5 spin up levels and 5 spin down levels, and the Fermi energy is sitting somewhere in this band structure. And this band structure is based on some parameterization by Slater-Costa, tight binding parameters. And what they argue is that the Fermi energy is sitting in this band structure in such a way that there's an odd number of right movers and an odd number of left movers, so that the system is ultimately topological. Okay. So now there is the cobalt story that I mentioned in the beginning, and you can convince yourself by spin polarized STM that both the d levels and the Shiba states are actually spin polarized apparently more or less uniformly along the chain. So this is along the chain, and the contrast, the fact that it's a single color contrast, basically means that these states have predominantly spin up or spin down character, and similarly for the Shiba states. Okay? So they have all the ingredients that you would need in order to have topological superconductivity. But if you look at the traces, and so here the red trace is the one that is at the end of the chain, and you see that at the delta tip, where you would expect these Shiba states, these Majorana states, there is no particular peak structure appearing, and that seems to be systematic. So why isn't there topological superconductivity in this system? Well, I cannot really give a definitive answer, but I can tell you a story that might be consistent with this. And so you can do the same Slater-Costa parameterization for these cobalt chains. And so this is shown here. It looks basically exactly the same as for the iron chains. Some of these levels are degenerate. So this one is a single one. This one is doubly degenerate, and this one is doubly degenerate. And then this is without any spin-orbit coupling. And then you can do it with spin-orbit coupling. And this is basically how the magnetization is oriented. These two things differ by how the magnetization is oriented relative to the direction of the wire. And if you assume that the direction of the magnetization is at some angle other than 90 degrees relative to the direction of the wire, then you see that you can easily get situations, and you assume that the cobalt, you'd have to fit 7 electrons per cobalt adatom into this band structure. The 4 s electrons kind of have to disappear into the substrate. Then you put your Fermi energy here, and then you have cases in which you have simply 2 right-moving and 2 left-moving excitations. This is only the positive case, and then there's it's symmetric to negative case. Okay. So in that case, if you have 2 right-moving and 2 left-moving excitations, then you would each one of those excitations would form a Majorana, and these Majoranas would hybridize and go away from 0 energy, and the system would be ultimately non-topological. That's a possibility. It's very easy to find these sorts of possibilities, and then it's also consistent with the iron chains, because if you make the same assumption about the s electrons going out into the substrate, then the iron Fermi energies would be sitting somewhere down here, and then you would have an odd number of right and left movers, and that should be very robustly topological. So that's a possibility for explaining these cobalt chains, and it requires really looking at the D level band structure. Okay, good. I have to close. So I started out by saying that this substrate is not very conducive to topological topological quantum computing, and the basic reason is that, as I tried to explain, is that all the energy scales here are really, in some sense, on the electron volt scale. At least whether you're topological or not, if you're in this region, which I believe is the relevant one for the experiments, then it's very robustly topological. You have to change parameters by huge amounts in order to get out of the topological phase or into the topological phase, depending on what you have. Whereas in the semiconductor wires, everything is on the level of a milli-electron volt, and this is much more conducive to being able to manipulate these Majoranas and doing something with them. Maybe the one way out might be that I didn't talk at all about the magnetic excitations that are also required here, the fact that you have this ferromagnetic ordering, and maybe by playing with this these magnetic properties, you might do something in the direction of topological quantum computation. But it seems rather complicated. And with that, I would like to thank you for your attention. Here are some of the things I talked about, and thank you for your attention.